In flight, the static pressure above the wing is lower than the static pressure below the wing. A component of the airflow moves sideways along the wing from the fuselage to the wingtip. This span-wise flow spills up, around the wingtip to where the lower pressure is, and flows back towards the fuselage on the upper surface of the wing. At the wingtips, the span-wise flow is the strongest. Strong vortices form here at the trailing edge of the wing. These are known as wingtip vortices, and they look something like this. These vortices require extra energy to generate, and this is bad for the aeroplane's efficiency. These vortices also contribute to drag, and here is how it works. The upward flow of the vortex is outside the span of the wing, but the downward flow is inside the span, behind the wing. The downward flow of the vortex deflects the relative airflow further down. This is called downwash. The deflection of the airflow downwards causes the wing to experience a local airflow. The direction of the local airflow is the average between the free stream relative airflow and the direction of the downwash. The aerodynamic force produced by the wing acts at a right angle to the local airflow. But since the local airflow is inclined downwards, the aerodynamic force is inclined backwards by the same amount. A component of the lifting force acts parallel to the free stream relative airflow and opposite to the direction of flight. This component acts in the same direction as the direction of drag. This component is undesirable, unavoidable, and it is known as induced drag.
Drag. Some situations where more lift is being produced would be flying at higher aircraft weights or maneuvering and pulling Gs, such as during turns or pull-ups. Okay, so now on to speed and how it affects induced drag. As we move slower, we have less airflow over the wings, but we need to continue producing enough lift to balance our weight. To do this at lower speeds, we need to increase the downwash. More downwash means more air being deflected, resulting in more or the same lift even though we are at a lower speed. But as far as induced drag is concerned, what really matters is that the increased deflection of the airflow at lower speeds means the lift is inclined further back, resulting in more induced drag. This is a bit counterintuitive, so it's worth taking a minute to think about. All things being equal, we get more induced drag at lower airspeeds. This is important because we operate at low speeds during takeoff and landing, and induced drag can play an important role during these phases of flight.